In this video, we will study some matrices whose eigenvalues are relatively easy to compute. Those are the upper and lower diagonal matrices and 2 by 2 matrices. Remember that if we have a upper diagonal matrix, that means that below the main diagonal we have zeros, right? All of these are zeros, and here we may have numbers. Then the determinant of this matrix, the determinant is just the product of the entries in the diagonal. Using this, we get that the eigenvalues of an upper diagonal matrix or a lower diagonal matrix are just the elements in the main diagonal. Let's see why. For example, if we have the matrix A, this matrix A, then the characteristic polynomial is just the determinant of A minus lambda I, and in this case, this is the determinant of the matrix 2 minus lambda, 3, 4, 0, negative 1 minus lambda, 4, 0, 0, 3 minus lambda. But using this property, since this matrix is upper diagonal, then this determinant is just the product 2 minus lambda, negative 1 minus lambda, times 3 minus lambda. And when we want to find the eigenvalues, we need to solve the equation characteristic polynomial equal to 0. But here it's easy because it's already factored. Then a product is equal to 0 if 2 minus lambda equals 0, if negative 1 minus lambda equals 0, or if 3 minus lambda equals 0. From here we get that either lambda is equal to, or lambda is equal to negative 1, or lambda equals 3. Then, as we mentioned before, if we have an upper diagonal matrix, then the eigenvalues are those entries in the diagonal. Here, for this matrix, the eigenvalues are lambda 1 equals 2, lambda 2 equals negative 1, and lambda 3 equals 3. Okay, let's move to 2 by 2 matrices. Let me start pointing out that if we have a matrix A equal to A, B, C, D, then the characteristic polynomial is given by lambda squared minus the trace of A times lambda plus the determinant of A. And if we want to solve the eigenvalues, we just need to solve this equation equal to 0. Remember that the trace of A is just the sum of the elements in the diagonal, A plus D. And the determinant of A is just AD minus BC. Let's compute the eigenvalues and eigenvectors and eigenspaces for this matrix B. For the matrix B, we have that the eigenvalues are lambda equal 3. The only element in the diagonal is 3. This is an upper diagonal matrix or lower diagonal matrix. Then we have this. We can also do it using the characteristic polynomial, and we can use this formula. We have to solve lambda squared minus the trace. The trace is 6 lambda plus the determinant 9 equals 0, and we get lambda minus 3 squared equals 0, which give us lambda equals 3. We can also do it with the definition. We can do the determinant of 3 minus lambda, 0, 0, 3 minus lambda, and that gives us 3 minus lambda times 3 minus lambda. And when we set up this equation equal to 0, we get that again, that lambda is equal to 3. Let's see what is the eigenspace. The eigenspace associated with 3 is going to be the null of the matrix A minus 3 times the identity. But in this case, this is the null of the matrix 3 minus 3 is 0, 0, 0, 0. What is the null of this matrix? Let's set up the equation. We get 0 x1 plus 0 x2 equals 0. 0 x1 plus 0 x2 equals 0. What are the basic variables? There are no basic variables. No basic variables. And there are two free variables. x1 and x2 are free. And that means that this null space is just going to be the whole R2. It's going to be the set of x1, x2, such that x1 and x2 are numbers. And then we can write this like x1 times 1, 0 plus x2 times 0, 1, such that x1 and x2 are numbers. And in this case, we have that the vectors 1, 0 and 0, 1 are eigenvectors. When we have a multiple of the identity, a diagonal matrix with the same number, and we have a 2 by 2 matrix, this is the only case in which the null space is going to be a two-dimensional space. It's going to have two free variables. Other than that, we are going to be able to describe the null space with only one free variable. And in the case that we are thinking about the real numbers, then that would be a line. Let's do this example. Again, for this example, we don't need to do the characteristic equation because we know that this is an upper diagonal matrix. Then we know that for the matrix C, lambda 1 is equal 1 and lambda 2 is equal negative 2. These are the eigenvalues of this matrix. Let's find the eigenspaces. Then to find the eigenspace associated with 1, we need to compute the null of the matrix A minus the identity. And this is the null of the matrix. When I subtract 1 in the main diagonal, I get 0, 4, 0, negative 2. And this, to find this null, we need to solve this system. 4x2 equals 0, negative 2x2 equals 0. We can see that this, when we do row reduction, we end up with only this equation, x2 equals 0 and 0 equals 0. That means that in this case, x2 is basic and x1 is free. And then the null can be written in this form. It can be written as x1 is free, then I write x1 and x2 is 0, such that x1 is a number. And this means that an eigenvector is going to be the vector 1, 0. As we mentioned before, only in the case that we have lambda 0, 0, lambda, if we have a 2 by 2 matrix of this form, then the null space of A minus lambda I is going to be a plane, and it's going to be the whole plane. There are two free variables. Two free variables. But if we are not in this case, we know that our null space only have one free variable. Then one way to proceed, instead of doing this computation here, is once we set up the equation, we just find a non-zero solution. Let's go in this way. Let's try to find a non-zero solution of this equation. This equation is telling us, please pick x2 equals 0. And this second equation is telling us, remember, pick x2 equals 0. That means that one solution would be x1 equal 1 and x2 equals 0. Remember that for an eigenvector, you are not allowed to pick 0, 0. That means that this is an eigenvector. But once we have that this is an eigenvector, then the null space is just going to be equal to x1 times 1, 0, such that x1 is a number. We don't have to pick x1. We can pick any other variable. We can pick t times 1, 0, such that t is a number. Then what I'm saying is that instead of computing the null, finding the basic variables and the free variables, we just need to pick a non-zero solution. And once you have a non-zero solution, the null is going to be the multiples of that non-zero solution. This is the null, and this is an eigenvector. Okay, let's find the other eigenvector. For lambda equal -2, let's do here this. For lambda equal -2, then we need to compute the null of the matrix A minus -2 times the identity, and this is the null of the matrix 1 minus -2, which is 1 plus 2, 4, 0, 0. And in order to find this null, we need to solve this system. 3x1 plus 4x2 equal to 0. And then we need to find a non-zero solution. Here I would like to stop and remind you that anytime we have an equation like this, a number times x plus a number times y equals 0, and you want to find a non-zero solution, then one choice is to make x equal to b and y equal to -a. This works. Let's see, if you pick x equal b, then you have a times b plus b times y, but y is -a, you get a times b minus b times a. This is one choice that works. And another possibility is to pick x equal to -b and y equal a. These are two possible choices that will give us a non-zero solution. Then, if we want to find the null associated with the eigenvalue -2 of this matrix, since this matrix is different from a multiple of the identity, we know that this null is going to have only one free variable. And then we just need to find a non-zero solution. We can make x1 equal to 4 and x2 equal -3. I'm doing this choice here. Then that means that an eigenvector is going to be the vector 4, -3. And therefore this null is going to be the space t times 4, -3, such that t is a number. Only one free variable. Notice that when you have a free variable, it doesn't matter if you call it s, if you call it t, if you call it x1 or x2. And this is the null space. Remember, if we're working with the real numbers, it's just a line. And then we have computed the two eigenspaces for this matrix. Let me do the other example. For the matrix D, we have that the characteristic equation is lambda squared minus the trace of D times lambda plus the determinant of the matrix equals 0. And this is lambda squared. What is the trace of D in this case? The trace of D is -2, and the determinant of D is -15 minus 20. Minus -20 will be plus 20 equal 5. Then we have lambda squared minus the trace, minus -2 it will be plus 2 lambda plus 5 equals 0. This equation, let's see, we cannot factor it. We will have to use the quadratic formula, and then we have that lambda is equal to -2 plus or minus the square root of b squared, which is 4, minus 4 times a times c over 2. And then this is -2 plus or minus a square root of -16 over 2. That means that we need to use complex numbers. The square root of -16 is plus or minus 2i, -2 plus or minus, 4i over 2. And then the answer is going to be -1 plus or minus 2i. Let's compute the eigenspaces. Then for lambda equal to -1 plus 2i. Then we need to compute the null of the matrix A, D minus lambda times the identity. Let's see what is this. This is the null of the matrix 3 minus -1 plus 2i, 5, -4, and here is -5 minus the lambda, -1 plus 2i. This is the null of the matrix 3 plus 1 is 4 minus 2i, 5, -4, and here we have -4 minus 2i. Then we need to solve this system. The system would be 4 minus 2i times x1 plus 5x2 equals 0, and -4x1 plus -4 minus 2i x2 equals 0. We need to solve this homogeneous system. But we know that this system has at least one non-zero solution, and that the whole null is just multiples of that non-zero solution. But how can I pick a non-zero solution of the first equation? I can use this. That means that I can take x1 equal 5 and x2 equal -4 minus 2i, which is -4 plus 2i. Then we conclude that, let me continue here. We conclude that the vector 5, -4 plus 2i is an eigenvector associated with the eigenvalue lambda equal -1 plus 2i. And what is going to be the null space? The null space of -1 plus 2i is just the multiples of that eigenvector. Let's see, we have that this is going to be the t's times 5 -4 plus 2i, such that t is a number. Actually, since we're working in the complex numbers, then we're going to say that t is a complex number. Okay, then this is the eigenspace. Notice that if you wonder if this is also a solution of the second equation, it should be a solution of the second equation. Let's check that. We have -4 times 5, right? Plus -4 minus 2i times x2, which is -4 plus 2i. Is this equal to 0? Let's check. This is equal to -20. Here is plus 16 minus 8i plus 8i minus 4i squared. And this is positive negative 4. These two cancel out. Negative 8i and 8i cancel out. Minus 4 and I squared is negative 1. Then we have that this is negative 1, and we have negative 4 plus 4 is equal 0. But you don't have to check this. We already know that the null is going to be the collection of vectors that are a multiple of a single vector. Then you just need to find that single vector, and then the eigenspace is just all the vectors that are parallel to this given vector. The other one is done similar. If you have here minus 2i, then the only difference is that here you will have a negative, and then you will end up with the matrix here with a plus, and here 5, and here with a plus, and then you will end up here with a plus, and here with a plus, and then you can pick x1 equal 5 and x2 equal negative 4 plus 2i, and then this is negative 4 minus 2i. And that means that the eigenspace would be the eigenspace of the matrix D associated with this negative 1 minus 2i is going to be the collection of vectors that are multiple of this eigenvector, which is 5, and here is negative 4 minus 2i, such that t is a complex number. Notice that this vector 5 negative 4 minus 2i is an eigenvector, and this is the eigenvector associated with this eigenvalue. Okay, we have finished example matrix D. Let's do matrix E. Let's start by computing the characteristic equation. We have lambda squared minus the trace of E lambda plus the determinant of E equals 0. In this case, the trace of E is going to be negative 6, and the determinant of E is going to be negative 7 plus 16, which is positive 9. Then we have that this is the equation, lambda squared minus negative 6, it will be plus 6 lambda minus plus 9 plus the determinant equals 0. Notice that we could have gotten the same if we do the determinant of the matrix E minus lambda I. This will be the determinant of the matrix 1 minus lambda, 8, negative 2, negative 7 minus lambda, and this is just 1 minus lambda times negative 7 minus lambda plus 16, and this is negative 7 minus lambda plus 7 lambda plus lambda squared plus 16. 16 minus 7 is 9. 7 lambda minus lambda is 6 lambda, and we have the lambda squared. We get the same result. This technique works for 2 by 2 matrices. Let's continue with this example. We can factor this as lambda plus 3 squared equals 0, and that means that the only solution is lambda equal negative 3. Then to compute the eigenspace, we need to find the null of the matrix E minus negative 3 will be plus 3 times I. And this is essentially the matrix that we get when we subtract negative 3 in the main diagonal. There will be 1 minus negative 3, it will be 4, 8, negative 2, negative 7 minus negative 3, it will be negative 4. And then to find this null, we need to solve the equation for x1 plus 8x2 equals 0, and negative 2x1 minus 4x2 equals 0. This is the homogeneous system that allows us to find this null. As we mentioned before, the solution of this is going to be multiple of a vector, and we can pick that vector to be x1 equal 8 and x2 equal negative 4. Then one possible solution is the vector 8, negative 4. This is an eigenvector. Notice that we can also pick any multiple of an eigenvector is still an eigenvector. We can pick 2, negative 1 as well. But then this is the eigenvector associated with this eigenvalue. In this case, this matrix has only one eigenvalue, and it's this. And then the null is just going to be the multiples of that vector. The t's times 2, negative 1, such that t is a number. This is the eigenspace of the eigenvector negative 3 for this matrix E.